Okay, so when you sit your combined science GCSE, you'll do 6 papers, and 2 of them will be chemistry papers, and there'll be obviously paper 1 and paper 2, and each of those papers comprises 5 main topic areas. Paper 1 is atomic structure and periodic table. That's the first one. Second one is structure and bonding. Third is quantitative chemistry. The fourth is chemical changes, and the fifth is energy transfer. So chemical changes is a huge topic. They're not all equal sizes, and we've been splitting it. We've split it into 3 different parts. So first of all, we looked at redox, and we looked at the extraction of metals. So we looked at reduction and oxidation. We were first introduced to those concepts. We looked at the reactivity series, and then we moved on to reactions of acids. Okay, so we looked at how salts were named. We looked at the different reactions between different bases and acids. We looked at what made an acid. We looked at the difference between strong and weak acids. And then the final part of the chemical changes topic is electrolysis. So we will certainly be looking backwards when we do electrolysis. We'll certainly be looking back at redox in particular. So those earlier sort of subtopics, if you like, that we've done will certainly play a part in our understanding of electrolysis. So I guess a good place to start is to think about what electrolysis actually means. So there are 2 parts to its name. So there's the electro bit, and that it refers to about electricity in this instance. And then the second part is the lysis bit, and that comes from a word that means split. So electrolysis is about splitting compounds using electricity, and the compounds that we are going to split primarily are ionic compounds. At least what has to be the case is that there has to be ions present for the possibility of electrolysis to be used. So electrolysis is a very important technique. It didn't exist until the invention of the battery. So Alessandro Volta invented the first battery, or it was he called it an electric pile, back in 1799. And then soon after, more powerful batteries were produced, and these were used to isolate undiscovered elements, and these elements were isolated because of electrolysis. So electrolysis became a new technique for extracting certain elements. So we use electrolysis today for a variety of reasons, many of which are very important. So it's used to extract certain metals. Essentially, any metal that's above carbon in the reactivity series is likely to be extracted by electrolysis. Chlorine gas, which is used for a variety of purposes, such as making bleach. It's how typically we get hydrogen gas. And with the increase in hydrogen-powered vehicles, that's becoming more important. And then also we get one of the raw materials, or one of the materials that we need to make soap, thanks to electrolysis. So it's a very important process. So we're focusing primarily on ionic compounds. There will be sort of one exception to this, really, that later in it, but it's principally ionic compounds that we're focusing on. And if we want to employ electrolysis on an ionic compound to actually therefore split that ionic compound, then the compound must either be molten or dissolved, okay, so in solution. So either with a state symbol of L for liquid to show it's molten, or a state symbol of AQ to show that it's dissolved. So I want you to just have a little think about why you think that needs to be the case. So if we're going to split an ionic compound, why do you think the ionic compound needs to be either molten or dissolved? And the clue, or the way for you to answer this question, is to think back to the second unit, structure and bonding. Think about the fact that these are ionic compounds, and think about the difference between a solid ionic compound and a molten or dissolved one, with reference to electricity. So just pause the video and have a little think about that, maybe jot a few ideas down on a piece of paper or something, and then we'll look at the reasons. Okay, so what it really boils down to is the fact that if we are to separate, or if we are to split our ionic compound, which is made up of different ions, then we need to be able to separate those ions, and therefore they need to be free to move. So in molten or dissolved form, ions are free to move. Okay, in a solid, they're not free to move. So they're in a lattice structure. They're held together by strong electrostatic forces of attraction. They aren't able to move, but once they're dissolved or molten, those ions are now free to move. We call a molten or dissolved ionic compound, we call it an electrolyte. So that's a term you may have heard of before. Okay, so we call them electrolytes, and in a solid form, because they're not able to move, they're not electrolytes. So the key point is, if we're to split and the ionic compound, if we're to separate its components, then we need those ions, we need them to be able to move, and that's why we need to have them in a molten, we need to have that compound in a molten or dissolved state. Okay, so what does that mean in practice? Well, this is how you need to think about how electrolysis is performed. As far as your exam is concerned, if they asked you to draw a diagram sort of showing the setup for electrolysis, you would need to draw something like this. So you obviously need a power supply. You need something that is going to result in an electric current. The reason for the bulb, it's just there. The bulb is just there so that you know that a current is actually flowing. All right, so that's all it's for. You're going to have these two things called electrodes. They are typically made of graphite, and the reason for that is, if you're going to have, well, essentially what we're going to be making is an electric circuit, so we need the current to flow all the way around the circuit, so we need everything to be able to conduct or carry charge. Also, charge can move, and graphite is used, if you remember back again in Unit 2, Structure and Bonding, when we did the allotropes of carbon, the different structural forms of carbon. A particular feature of graphite was the fact that it had delocalized electrons, and so these could move through the structure and carry charge. So these positive and negative electrodes are typically made of graphite. Obviously, our electrolyte, as we've already said, has to be molten or dissolved. Okay, and then when we turn on the power supply, what's going to happen is one of the graphite rods, one of the electrodes, is going to be positive, and the other is going to be negative. And now I'd just like you to think that once that happens, once we have a positive electrode and a negative electrode, I want you to just think about what you expect to happen, or what you think might happen to those ions that are molten or dissolved. So you can see in this diagram we've got some particles with a minus charge, some particles with a positive charge. They're just supposed to represent positively and negatively charged ions. So when we turn the power supply on and we get that a positive and negative electrode, what do you expect to happen? So I'll just pause for a minute. Maybe you pause the video, have a think about it, and then we'll discuss it. Okay, so one of the key things about charges, which you might realise from your physics, that opposite charges attract. Okay, so this is electrostatics. In fact, this is, if you think about it, we know that already from our ionic compounds. We have ions of opposite charges attracted to each other. This is a strong electrostatic attraction, and is one of the reasons why it requires a lot of energy to melt an ionic compound. So when we look at our ions, what we're going to find is the negative ions are going to be attracted to the positively charged electrode, and then the positive ions are going to be attracted to the negatively charged electrode. Okay. And when they get to the electrode that they're attracted to, depending on whether they are the positively or negatively charged ions, they are either going to accept an electron or electrons, or lose an electron or electrons, depending on the charges. And when that happens, they are going to become, what we say is they are discharged. It's quite a weird word, I guess, but we say that they are discharged, and the result of that is that we get the original element, or we get the element. So basically we are reversing the process we looked at when we looked at the formation of ionic compounds back in Unit 2, when we had the elements and they either lost or gained electrons to form an ionic compound. Here basically we're reversing the process. The ions are either losing or gaining electrons, but to become the elements. So we're sort of going backwards. Now positive ions are also known as cations, so you just need to be aware of that. So positive ions are called cations, and negative ions are called anions. And cations are attracted to the cathode, and anions are attracted to the anode. And to repeat, when the ions reach the electrodes, they are discharged. Okay, so let's try and understand this discharging a little bit better. So here what we've got is we've got a chloride ion. Okay, so here's our chloride ion, and it's being attracted to the positive electrode. And then when it gets there, what's going to happen is that the electron, the sort of extra electron, the electron that makes it a negatively charged ion, is going to be lost, and it's going to go, the electrode's going to take it, the positive electrode's going to take it, and then if we do that times 2, what we then end up producing, this is the discharge, is, and I'm just going to draw the outer shells, we are going to make a chlorine molecule. Okay, so the chloride ions have been attracted to the positively charged electrode. That's because the chloride ions are negatively charged, the electrode is positively charged, opposite charges attract. When they've reached the electrode, each chloride ion has lost 1 electron, and the positive electrode has accepted that electron. In doing so, two chlorine atoms have come together to form the chlorine molecule, because that's how chlorine exists in an elemental form. It's a diatomic molecule, and so we get chlorine produced, and essentially we've liberated the element from the original mixture, from the original ionic compound. Final thing to say is that because the chloride ion lost an electron, the process that's taking place at this electrode is oxidation. So remember our oil rig mnemonic, and oxidation is the loss of electrons. Chloride ions are losing an electron each, so they are being oxidized. The chloride ions are being oxidized. If we look at the other electrode, the negative electrode, the sodium in our example here is a positively charged ion, so that's going to be attracted to the negative electrode. And if it's a negative electrode, that means it has quite a lot of electrons on it, sort of rich in electrons anyway. When the sodium ion reaches that electrode, what's going to happen is it's going to accept, okay, an electron. So then what we get as the product there is elemental sodium. So to confirm, what we're saying is when ions are discharged at the electrodes, they return, or they become the uncharged atom of that element. So they become that element. So just thinking about the process like we did on the previous slide, here each sodium ion is gaining an electron, and we know that reduction is the gaining of an electron. So the process that's taking place at the negative electrode is reduction. because a positively charged ion is gaining an electron or electrons. So just briefly on a little mnemonic that can help you remember which electrode is which. This I quite like this. Panic, positive anode, negative is cathode. And if you then need to remember which are anions and which are cations, anions are always attracted to the anode and cations are always attracted to the cathode. So if it's a positive anode, then we've got negative anions, and if negative is cathode, we've got positive cations. And so that's just a useful way perhaps to remember the charges of the electrodes. And this is just to make the point that in electrolysis we have a redox process taking place, so we have oxidation and reduction taking place. And just again another way to sort of try and, or useful way hopefully, to try and remember which is which. So oxidation, loss of electrons, that's going to take place at the positive electrode, because the positive electrode is going to accept those electrons, and reduction is the gain of electrons, so that's going to take place at the negative electrode, because that's going to supply the electrons that are gained. So just remember that this does refer back to the first part of the chemical changes topic that we did, which was redox, where we had both reduction and oxidation taking place at the same time, and that's all to do with the loss and gain of electrons. Okay, so I want you to just have a look at these sentences, and pause the video, and then I will fill in the answers, but I would like you to try and think of the answers before I do that. So like I say, pause the video and have a think about that. So there are the answers. I just pause the video so that you can check your answers against that. I'm not going to talk them all through, so just pause the video and check your answers against these. So just a quick refresher. Why was it necessary for the ionic compound to be molten or dissolved if we're going to do electrolysis? You just think about that for a second. Well, it was so it can conduct electricity. So can you remember why an ionic compound only conducted electricity when molten or dissolved? Just have a little think. Well, if an ionic compound is to conduct electricity, then there has to be a flow of charge, and it's the ions that carry the charge, and if there's to be a flow of charge, the ions have to be able to move. So the reason that we have to have a molten or dissolved ionic compound for electrolysis to work is because the ions must be free, or need to be free, to move, and it's only when they're molten or dissolved can that happen. Okay, so we're building on a lot of the knowledge that we've done in other parts of the course, and one thing that is particularly pertinent to this topic is knowing the charge and the symbols for the ions that are found in any sort of ionic compound that we could be given. So here are just 8 ionic compounds that we could be looking at, we could be considering, and it's important for us to recognise, to appreciate what those ionic compounds are actually made of, what their ions are, basically. So I want you to pause the video again, and I want you to think about what ions are present in magnesium chloride, in sodium bromide, in calcium chloride, and so on. Maybe again jot your answers down on a bit of paper so that you're sort of committing yourself to an answer, and then we'll look at the answers in a second or two. So pause the video. Okay, so here they are. So I'm just going to just cover a couple of them, or talk about a couple of them. So we've got magnesium chloride, and so our metal is magnesium, or non-metal is, well, is chloride. Magnesium is in group 2, so any ion that it forms is going to be a 2+ ion. Chlorine is in group 7, so its chloride ion is going to be a -1 charge. Just talk about aluminium oxide. Aluminium is in group 3, so if it forms an ion, it's going to be a 3+ charged ion. Oxygen is in group 6, so the oxide ion is going to be 2-, because it would have had to have accepted 2 electrons to get its full outer shell. Just down on the bottom left here, copper 2 chloride. So Copper's a transition metal, so we can't tell. It doesn't have a group number, so we don't have a group number to help us work out the charge, and that is where the Roman numeral becomes important, because basically that Roman numeral is telling us the charge on that copper ion. So it's telling us it's a 2+ charge copper ion. Something else to look at, we've got sulfate, both in sodium sulfate and magnesium sulfate. So this is an example of a polyatomic ion. That means it's an ion made up of many atoms, or more than one atom. I'm afraid you just have to learn it. You have to learn that sulfate has the formula SO4 and the charge 2-. And the same with nitrate. It's another polyatomic ion. You just have to learn it. So nitrate is NO3, and the charge on that ion is 1-. So the next thing maybe would be a good idea for us to do is to now determine the overall formula of these compounds based on these ions and their charges. So again, I want you to pause the video. I want you to write on the paper what you think the full formula for magnesium chloride is, for sodium bromide, for calcium chloride, etc. And then you can compare your answers with mine. Okay, so pause the video, please. How many did you get right? Hopefully all of them, but if you're still having problems with this, then now is not the time. I mean, this video is not the moment to truly sort it out, but please do get in touch with me, and we'll try and work out a way of fixing that. Okay, so let's just remind ourselves again of the basic process. We are effectively producing a circuit. It becomes a complete circuit when our ionic compound is molten or dissolved, because the ions are free to move and carry charge. And remember that a current is a flow of charge. So we have our power supply. We have a lamp just to show that we do have a complete circuit. And we've got these two electrodes, one of them which is positive, one of which is negative. And the oppositely charged ions are attracted to these electrodes. So the positive charged ions are attracted to the negative electrode, and the negatively charged ions are attracted to the positive electrode. Okay, and then what happens is the positive ions are reduced, so they gain electrons. The negative ions are oxidized, so they lose electrons, and we get the uncharged elements produced at those electrodes. So let's apply that knowledge to some real examples. So we've got our electrolysis equipment set up. We are going to have magnesium chloride as our ionic compound here. So the first thing that we just need to be confident in is that we know what our ions in our solution are. So from earlier we know it was Mg2+, and we know it's Cl-, and we know that the positively charged ions are going to be attracted to the negative electrode, and the negatively charged ions are going to be attracted to the positive electrode. Okay, so when those magnesium 2+ ions reach the electrode, what happens? Well, they are reduced by gaining 2 electrons. So remember, reduction is the gain of electrons. They need to gain 2 electrons to go back to their uncharged atom form. So they are reduced by gaining 2 electrons. And we can represent this process using an equation. So if you remember in the redox, we did these things called half equations. So what have we got happening? So we've got the Mg2+ ion, and it reaches the negatively charged electrode, and it gains or accepts 2 electrons. And then what do we get produced? We get produced our magnesium metal. So we actually observe, we actually see the magnesium being discharged, or the Mg2+ ions being discharged to form magnesium metal, and we would begin to see that metal coating the electrode. Okay, so let's now look at the positive electrode. So here, chloride ions, which are negative, are being attracted to the positive electrode. When they get there, they are each going to lose 1 electron. So they're being oxidized, because remember, oxidation is the loss of an electron. and we're going to be forming the element chlorine. Now, if we remember, chlorine is a halogen, and one of the things that we know about halogens is that they exist as diatomic molecules. So we have to bear that in mind when we write the equation representing this process. So we know that we've got chloride ions, and we know that we're making chlorine, and we know that chlorine is Cl2. So the first thing that we need to do is make sure that we have the same number of chlorines on both sides. We currently have 1 on the left and 2 on the right, so I'm going to put a 2 there. And then the next thing that we need to balance is the charge. So at the moment we have 2 1- ions on the left, so that's a total of -2. And then on the right we've got, well, it's an element, so it has no overall charge. So we need to make that also -2. And don't forget that each chloride ion was losing 1 electron, so we show that by writing 2e- there on the right. So our half equation is 2Cl- goes to Cl2 plus 2e-. Now, chlorine as an element is a gas, so we're actually going to observe, we've got to observe that formation, the formation of a gas. So we're going to see effervescence around the positive electrode, and that is going to show us that a gas is being produced. So I think the last thing for us to do is to perhaps write the overall equation. I'm going to try and do that in the limited amount of space I've got left here. So we start with magnesium chloride, and during the process of electrolysis we get magnesium metal formed and chlorine gas formed. So we are going to get magnesium goes to magnesium plus chlorine. What we can actually think about what type of reaction this is an example of. So we have only one reactant, or only one chemical substance on the left-hand side, and we have more than one on the right, and this is an example of a decomposition reaction. So a substance is being broken down into simpler parts. So it's an example of a decomposition reaction. Okay, so we're going to look at another example. So again, let's think about what ions we've got present. So we're looking here at sodium chloride. So we have sodium ions and we have chloride ions, and the sodium ions are going to be attracted to the negative electrode, and the chloride ions are going to be attracted to the positive electrode. So the sodium ions are attracted to the cathode. When they get there, they gain an electron, which means they're reduced. We can represent that with a half equation where we show the sodium ion plus an electron, that's the one it's gaining, produces sodium metal, the element. Because it is a metal, we're going to see a metal deposit form around that negative electrode, so we're going to see the sodium forming. At the positive electrode, it's exactly the same as before, because we've got the same ion, we've got chloride ion. So those chloride ions are negatively charged, they're attracted to the positive electrode. Here they're going to be oxidized because they're losing 1 electron. Because it's going to form its element, chlorine, which is a diatomic molecule, we're going to require 2 chloride ions to lose an electron each to produce those, or to produce that halogen molecule. So we can represent that with our half equation. 2 chloride ions goes to a chlorine molecule, and then 2 electrons are lost or released. And then, because chlorine is a gas, we would see some fizzing around the positive electrode, and we would observe that gas being produced. So thinking about the overall equation here, we started with sodium chloride, and we're making sodium and chlorine. So again, we've got only one chemical substance on the left-hand side. On the reactant side, we've got 2 on the right. So we're breaking down sodium chloride into its constituent parts, sodium and chlorine. This is a decomposition reaction. Okay, so here's a final example. So our ionic compound is zinc bromide. So let's think about what ions are present there. Well, we've got zinc ions, and we've got bromide ions, and the zinc ions are going to be attracted to the negatively charged electrode, and the bromide ions to the positively charged. And then I want you to maybe pause the video and think about what we've done on the previous 2 examples, about how we've described what's happening at each electrode and what we would observe, And I would like you to just pause the video and have a think about what you imagine will be the case in this example here. So at the negative electrode, the zinc ions are attracted to it. Here they're going to gain 2 electrons each, so they are being reduced. And we can show that half equation, Zn2 plus 2e minus goes to Zn. So just a reminder that the e minus represents an electron. Because zinc is a metal, we're going to see solid zinc form around the negative electrode. At the positive electrode, we've got Br minus ions, so they're going to be attracted to the positive electrodes. Here they are just as with the chloride ions, they're being oxidized, so they're losing 1 electron. They're going to make bromine, and we all know that all halogens are diatomic molecules when they're in elemental form. So for every bromine molecule, we need 2 bromide ions. So we represent that with the half equation. So we have 2 bromide ions becoming bromine, and 2 electrons are lost. So bromine is a liquid at room temperature. However, here we're doing molten electrolysis, and we've melted an ionic compound. And we know that ionic compounds have high melting points. That was something that we learnt in the second unit in structure and bonding. So the electrolysis here is happening at a high temperature, and that temperature is easily high enough for the bromine to be evaporated and to become bromine gas. Bromine is actually quite a volatile element. Its boiling point isn't much higher than room temperature, so certainly at these temperatures it would have turned into a gas. And we would observe that at the positive electrode we would see fizzing, we would see effervescence, we would see that bromine was being produced. So we're going to sort of summarize what we've just been doing on those previous 3 examples by looking at another example. So we have lead bromide, so that is made up of lead 2 plus ions and bromide ions, Br minus ions. So we're going to start with looking at what happens at the negative electrode. So pause the video and try and list all of the things that you could write about what was happening at negative electrode. That includes what you would actually observe, what's happening in terms of the electrons, how could you represent that change using a half equation, so how could you explain what you observed. So try and think of all of those points, and then we'll have a look at it together. So let's pause the video and have a think. Okay, so we know it's the lead ions that are being attracted to the negative electrode. And when they get there, they're going to each gain 2 electrons. So we can show that with the half equation. So we have the before and the after, right? So before we've got lead 2 plus ions, and then after we've got lead, the metal. And for that change to take place, the lead 2 plus ions have to gain 2 electrons. So we have the plus 2e minus on the left. We're making lead. Lead is a metal. Metals have a lattice structure. They have metallic bonding. So what we're going to observe is solid deposits of lead around that electrode, around the negative electrode. So as a general rule, and this is in terms of observation, and quite often in exam questions you can be asked what would you observe. If you are getting metal ions, if you ever have metal ions reduced, and this also happened in the redox unit, if you have metal ions being reduced, so they're becoming the metal in its elemental form, then you will see solid deposits around that negative electrode. When we consider the positive electrodes, we know that it's the bromide ions that are being attracted to it. They are a 1 minus charge, so when they get to the positive electrode, they're each going to lose 1 electron. However, we know that bromine doesn't exist as a lone atom. We know that halogens exist as pairs of atoms, so we've got 2 bromide ions becoming bromine, so we represent that half equation as 2Br minus goes to Br2 plus 2e minus, so that 2e minus on the right hand side are the electrons that are being lost from those 2 bromide ions. And so that's just the key thing that you could forget, is that whenever you have a group 7 element, being oxidized, then, and it's going back to the original elemental form. That element is going to be a diatomic molecule, so you've got to make sure that you have 2 ions for every 1 diatomic molecule. So in the higher tier part of the course, so to do the higher paper, one of the things that you've got to be prepared to do are half equations. So remember, we've done these briefly in the redox topic. So they are a very useful way of showing how many electrons either an ion loses or gains during oxidation or reduction. We know that positive ions will be reduced because they'll gain electrons. And so all of the examples here are positive ions being reduced. So these are partially done for you. What you need to do is fill in the blanks. So I want you to pause the video, have a think about what you would put in each blank to make sure that this each equation is balanced, and they have to be balanced in 2 ways. They have to be balanced in terms of the element, and they have to be balanced in terms of charge. So both sides of the equation have to have the same overall charge. So pause the video and have a think. Okay, so in the first one, we've got Mg2 plus blank goes to Mg. So we've got the right number of Mgs on both sides. There's 1 on each side. When we look at the overall charge on the left, at the moment it's 2 plus, and on the right it's 0, because remember, all elements have an overall charge of 0. So we need to bring down the charge on the left. We need to bring it down to 0, and we do that by adding 2 electrons. So it's like saying plus 2 minus 2 equals 0, which it does. If we look at the next one, 1 sodium on the left, 2 sodiums on the right, that's fine. We've got a 1 plus charge on the left, a 0 charge on the right. We need to bring down the left by 1, so we're going to add 1 electron. We've got the right number of aluminiums in the third equation. We've got 1 aluminium on both sides. We've got an overall charge of 3 plus on the left at the moment and 0 on the right. So we need to bring down the left by 3, so we're going to add 3 electrons. When we look at the final one, we've got actually only 1 hydrogen on the left at the moment and 2 hydrogens on the right. So the first thing we need to do, so always do the elements first. We've got to put a 2 in front of the H+. So now we've got 2 hydrogens on the left and 2 hydrogens on the right. And then when we consider the charge, the overall charge on each side, we've got to take into account that large number before the H. So we have 2 times plus 1, right, in terms of our charge, because we have 2 H+ ions. So we've got an overall charge at the moment on the left of plus 2, an overall charge on the right of 0, so we have to bring down the left by 2, so we add 2 electrons. Similarly, when we look at half equations in which negative ions are discharged, so the negative ions are being oxidized and therefore losing electrons, it's exactly the same process. We first of all make sure that we've balanced the element, and then we start to look at the charge. So if you could pause the video and have a think about what's missing in each of these half equations, and then we'll look at the answers. Okay, so on the first equation, we have at the moment 1 chlorine on the left and 2 chlorines on the right. So the first thing that we need to do is we need to put a 2 before the Cl-. Then when we look at the charge, we've got -2 on the left and 0 on the right. Now, we can only ever add electrons, so we can only ever bring the charge down. So we have -2 on the left, 0 on the right, so we need to bring that 0 down to -2, and the only way we can do that is to add 2 electrons. We've got 1 bromine on the left and 2 bromines on the right. So we're going to have to put a 2 in front of the Br-. Again, we've got a -2 charge on the left and a 0 charge on the right. All we can do is decrease charge by adding electrons. So we need to bring the right-hand side down from 0 to -2. So we're going to add 2 electrons. When we look at the third equation, we've got 1 iodine on the left and 2 on the right. So we have to put a 2 in front of the iodide ion, And then it's exactly the same as before. You can see a pattern whenever you've got a halogen. It's 2 of the halide ions goes to the halogen molecule plus 2E minus. And then the last one. Okay, so this is an equation, half equation, that's going to feature in another part of the electrolysis topic. But we're just going to look at the half equation now. So let's just check the elements. So we've got oxygen and hydrogen. So on the left, we've got 4 OHs. So we've got 4 oxygens and 4 hydrogens on the left. And then in the H2O, we've got 2 H2O molecules and an O2 molecule. So we actually have 4 hydrogens and 4 oxygens on the right also. So we're fine there. So let's think about overall charge. So on the left, we've got hydroxide ions. They have a 1- charge, but we've got 4 of them. So overall, we have a -4 charge on the left. And on the right at the moment, we just have water, which has no charge, and oxygen that has no charge. So we have 0. So we've got -4 on the left, 0 on the right. All we can do is decrease charges, like bring them down if you think of a number line. So we have to bring the right-hand side down from 0 to -4. And the way that we do that is we add 4 electrons. Okay, so we've introduced electrolysis, we've explained the basic principle of it, and we've then focused particularly on electrolysis of molten compounds. So if you remember early on in the video, we said that electrolysis could take place if the ionic compound was either molten or dissolved. So we've focused on molten ionic compounds in this video. We're going to have another video to consider the electrolysis in aqueous ionic compounds. But before you get to that point, what I'd like you to do, please, is to complete the practice questions I've sent you. So these ones here, there are level 4, level 6, level 8. I would like you to choose the appropriate level for yourself, please. And then I would also like you to attempt the half equations for electrolysis sheet. And then finally, there are further questions sort of classed as homework, but I mean, we're just doing work at home anyway, aren't we? Again, there are level 4, level 6, and level 8, and I would like you to choose the appropriate one for yourself, please. If you have any questions, you know where I am, and we'll sort them out. All right, thank you.